gentlemen, welcome back to our plenary program, which today again kicks off with an exciting panel. The title of this panel is New Opportunities Benefit Human Spaceflight on Earth, in Space and Beyond. And this is a panel organized by the Chinese Academy of Sciences. We've heard during this week already a lot about the outstanding and stunning achievements of China in robotics exploration. Now, this panel will focus on the progress and future plans for China's scientific research and utilization in human spaceflight. The panel will also discuss global collaboration efforts, highlighting cooperative activities centered around microgravity facilities, including space stations, spacecraft, parabolic flights, and much more. And to lead you through this discussion, it's my great pleasure to introduce the moderator of this session, Mengguin Chen. She is the acting director of the International Cooperation Center in the Technology and Engineering Center for Space Utilization of the China Academy of Sciences. Please give her a warm applause. Welcome with a warm applause.
Thank you very much, Dr. Festinger. Distinguished guests, ladies and gentlemen, welcome to our plenary session, New Opportunities Benefit Human Spaceflight on Earth, in Space and Beyond. This session is organized by CMSA and hosted by CSU. I'm privileged to chair this session. If you arrived here earlier, you may just saw the video, and China has just completed the assembly the Tiangong Space Station in 2022, entering a new stage of operation and utilization. Thousands of experiments are planned. Various international cooperation activities have been conducted, fully demonstrate responsible space for sustainability. Today's panel will deliver the vision of new opportunities benefit human spaceflight in various ways provided by China as well as their collaboration partners. To be short, we can start the session now. Firstly, Mr. Lin Xiqiang, the Acting Director General of CMSA, wants to give his welcome address to the guests through the video. He cannot participate in person because of the launching mission preparation. Please.
Distinguished delegates, ladies and gentlemen, good morning. Firstly, on behalf of the China Manned Space Agency, I warmly welcome you all to this special session on China's human space development. I'm sorry that I cannot join you in person due to preparations for the China Space Station annual missions. Nevertheless, I'd like to congratulate on the successful convening of the 75th International Astronautic Congress and express my heartfelt gratitude for your ongoing attention and support for China Manned Space Program. Later, 2022 marked a significant milestone for us with the completion of the in-orbit construction of China's space station. This achievement realized the three-step development strategy set by Chinese government in 1992 and ushered in the station's utilization and development phase. Since 2023, we have conducted 3 crew rotations, 2 cargo resupply missions, and 5 spacewalks. As for the space science and application, we have carried out nearly 200 on-orbit experiments and several Tiangong classroom popular science activities. Plus, with United Nations, we are steadily implementing international cooperation programs. In all, the CSS is in the stable status and operating efficiently. Our on-orbit astronauts are in good condition, and ground support is robust. The station serves as an exceptional platform for advancing China's space science, technology, and utilization, with its benefits becoming increasingly evident. Meanwhile, our government has greenlit the lunar landing phase of our human lunar exploration program. We aim to land Chinese on lunar before 2030. Currently, we are making steady progress in developing key systems, including the Long March 10 carrier rocket, Mengzhu human spacecraft, Lanyue lunar lander, and lunar activity spacesuits. Major flight products are undergoing prototype production and various tests. In the future, China shall never cease from space exploration. As a key player in humanity's quest to understand the universe, we aim to contribute significantly to the peaceful use of space for the benefit of all. We warmly invite you to engage more deeply with China's manned space and welcome participation from all nations and regions dedicated to the peaceful use of outer space. Together, we will promote prosperity and advancement of human space endeavors. Thank you for your attention.
Okay, thank you, Mr. Lin. CMSA has deep cooperation with UNOOSA. In 2019, they have jointly approved the first round of cooperation projects on China's space station. Please allow me to introduce Mr. Andrew Peebles to give his address to this session. He is the External Relations Officer for UNOOSA, responsible for communications and partnerships with UN member states. Thank you.
So good morning, everybody. Your Excellencies, distinguished delegates, thank you for extending an invitation to the United Nations to speak to you today. At the UN Office for Outer Space Affairs, we regularly get questions about why do we go to space when there are so many problems here on Earth? And from our perspective, when we receive these type of questions, it's clear that we as a space community need to do more to communicate the benefits and make the case for space. The answers to why we go to space are numerous. We as a sector, we know them. It helps us answer the big questions, why we're here. How did it all begin? Are we alone in the universe? What comes next? And most importantly, can we make the lives for the people on this planet better? Ultimately, and throughout our common history, we've been a species of explorers. The research that is being conducted on Tiangong, the International Space Station, and other platforms that are currently being developed have real-world applications that address global challenges such as climate change, food security, health, disaster resilience, and many, many more. Similarly, experiments in microgravity physics have potential to unlock new materials, technologies, and processes that could revolutionize life here on Earth. Distinguished delegates, the UN Office for Outer Space Affairs was proud to have entered into an international collaboration and partnership with the China Manned Space Agency in 2018, through which 7 teams from multiple countries, ranging from China, Germany, India, Italy, Japan, Kenya, Mexico, Peru, Poland, the Russian Federation, Saudi Arabia, Spain, and Switzerland, have all been awarded opportunities to conduct their experiments on board the China Space Station. So we have to ask ourselves, why are opportunities such as this important? From the United Nations perspective, these Access to Space for All initiatives have proven to be successful hooks or catalysts, if you will, for kickstarting or enhancing the space ecosystems and economies of countries all around the world. And from our perspective, we don't take these opportunities for granted. For every extra gram of weight that is carried on board one of these opportunities into space when it's launched, we know the costs. So for that, we're very, very grateful for the opportunities that are presented to us by CNSA and others. Similarly, through other grassroots initiatives and projects with universities and startups, the NUSA has a track record of assisting countries to access the benefits of space for the peaceful uses of outer space and for the benefit of their citizens. These projects not only have been sources of national pride and prestige, they've been catalysts for the creation of space agencies, space laws and policies, promoting STEM education in countries, and also the uptake of space data, services and technologies. So distinguished delegates, we at the UN, we're very excited. We're very excited to see what comes from the experiments that will be carried out over the next few years. And we're excited to see the type of lessons that will be learned that maybe from some of these experiments to advance humanity's exploration of the cosmos, settlement on other worlds, and maybe, just maybe, a new spin-off technology that we might all be using as a spin-off technology or a consumer product in the next few years. So with that, I would thank you and thank the organisers and wish you an interesting panel. Thank you.
Thank you, Mr. Peebles. The Chinese Academy of Sciences is a linchpin of China's drive to explore and harness high technology and the nature sciences for the benefit of China and the world. It is also the important system responsible for the scientific research and utilization. I would like to invite Mr. Sun Hui to give his address to this session. Mr. Sun Hui is the Director of Division of International Organization Programs, Bureau of International Cooperation of Chinese Academy of Sciences.
Distinguished Dr. Christine Fechtinger, Executive Director of IAF, Mr. Andrew Peebles, External Relations Officer of NUSA, distinguished guests, ladies and gentlemen, good morning. It's my great pleasure and privilege to attend the plenary session, New Opportunities Benefit Human Spaceflight on Earth, in Space and Beyond, of the 75th International Astronautical Congress. On behalf of the Bureau of International Cooperation, Chinese Academy of Sciences, I would like to extend my warmest welcome and sincere regards to all of you present here today. As we stand at the threshold of a new era in space exploration, I'm very delighted to share insights of our commitment to the peaceful use of outer space. The China Space Station, CSS, representing our nation's relentless pursuit of scientific progress and technological innovation, is a significant milestone in human space science and utilization. It embodies our vision of a future where space serves as a platform for international collaboration, discovery, and the advancement of knowledge that benefits all humanity. As a leading national research institution of natural sciences and technology in China, CEST is comprised of a comprehensive research network and merit-based learning society and a system of higher education training next generation of scientists and engineers. CEST has been always at the forefront of science. Over the past decade, it has successfully launched and operated numerous satellites and space labs such as MiCo, Einstein Probe, Tiangong 1, Tiangong 2 space labs, and the National Space Laboratory, CSS. Significant breakthroughs have been made in the fields of space science, exploration, and new utilization technologies. CEST attaches great importance to international cooperation with our partners, with the objective of addressing shared challenges pertaining to green, sustainable, and inclusive development. CEST Institute of Technology and Engineering Center for Space Utilization, CSU, has leading the Space Utilization System China Manned Space Program, CMSP, and providing scientific and technical managerial support for CMSP, established extensive collaborative relationship with international partners, including IF, UNUSA, ESA, Italian Space Agency, and so on. So we are convinced that the significance of scientific collaborations lies in the collective wisdom and concerted endeavor of all the participants. This plenary session will promote the mutual understanding of the peaceful use of outer space and the collaboration among members of the international network. CEST will continue our efforts to support international cooperation in space exploration, which would contribute to the prosperity and well-being of mankind. With the above, I would like to express my gratitude to all the participants for your dedication, passion, and tireless efforts in advancing the field of space. I wish the plenary session a great success. Thank you very much.
Thank you, Mr. Sun. Now, please allow me to welcome today's 5 speakers on the stage and take a seat here. Dr. Li Ming, Chairman of Science and Technology Committee of China Academy of Space Technology. Professor Zhong Hongen, the Deputy Chief Designer of Technology and Engineering Center for Space Utilization, CEST. Dr. Serena Perilli from ESTI. She is responsible for the orbital and suborbital human spaceflight activities. Dr. Vladimir Pletzer. He worked for 30 years at ESA's SDAC, and now he is the Director of Space Training Operations in Blue Abyss. Dr. Giuseppe Zumo. He has been a researcher in ENEA Italy. Now he is also the CEO of Inquatro. Okay, welcome our speakers. They will deliver their presentations, and maybe I will ask some questions if time is allowed. Then please welcome our first speaker, Dr. Li Ming, please.
Distinguished audience, ladies and gentlemen, it's really a great pleasure and privilege to have this opportunity to make presentations. And in my presentations, I will talk about briefly the story about the Chinese manned space missions and also the opportunity for international cooperation. You know, the Chinese space station complete its construction in orbit in 2022. These space stations can support 3 astronauts for the long-term missions, and also it can support maximum 6 astronauts for the short-term missions, for example, for the rotations and shift change. The space station consists of 3 major modules, including the core module, another 2 experiment modules with a cargo ship for supply, and with the Shenzhou manned ship for transportation of the astronaut. With nearly 18 flight experience, the transportation system Shenzhou manned spaceship is reliable and on time, is a guarantee. We have already conducted about 16 EVA activities with a maximal EVA time about 8.5 hours. This is the view from panorama camera, external cameras. This is the view from internal cameras through the window. This is just animations for the rendezvous and docking. As to the capacity and interface, we provide not only the external service and payload, but also we provide the internal payload support. For example, for the external support, we provide nearly 50 payload adapters, which is very good for the explorer mission and also for the observation missions. For the internal support, we provide the payload rack, nearly 25 racks, which is suitable for the biology studies, microgravity studies, and also the space material studies. This slide just shows some example we have finished in the space station, some technology tests and demonstrations. For example, the liquid metal thermal management test and the Stirling thermoelectric conversion test, and so on. Besides the space stations, we still have another means for the experiment. That is the cargo ship. Since the cargo ship has a very heavy-duty abilities, and it can provide additional abilities for the space experiment. One of the interesting application is to using the cargo ship for the release of the CubeSat. In this slide, I'll give you just 3 examples using the cargo ship for the release of CubeSat for the commercial company. Another one is for the MiCo high school university, high school student satellite. Last one is for university-made satellite. I think it's a Earth observation satellite with a resolution better than 1 meter. In the future, we will try to upgrade our facilities. And the first is to upgrade an extension of China's space station, the core modules. With this purpose, we try to upgrade the space station from the T-shape, present is a T-shape, to the future, the cross shape, or you may also call it the double team shape. And also, we'd like to upload more space science experiment tracks, racks, and also a large extravehicular experiment, and to expand the application scale. Another upgrade is develop the reusable spaceship. This is the next generation manned spacecraft for lunar mission and also for the space station missions. With this spaceship, we can support 3 astronauts for the lunar missions, and also the 7 astronauts for the LEO space station missions. The returner capsule is specially designed for reusable. Last one is the CEST, Chinese Space Station telescope, which has very large optical cameras featuring both a large field of view and high image qualities. Primarily, it takes with a large-scale astronomy surveys, and it also open for international communities, especially on the data analysis. Chinese government has officially kicked off the manned lunar exploration missions. In strategy, we divided the development into 3 phases. First phase is called demonstration phase, which will be used for the demonstration of key technologies. And this phase has already finished 2 years ago. Now we are moving to the implementation phase. That is to send a technonaut to the moon and return safely in this decade. The next phase will be the research and development. We will carry out a systematic and continuous human lunar explorations and to explore and develop technologies of in situ resources utilizations. This is a typical process for lunar missions. First, we will launch the lander and also the manned spaceship using the Chinese Long March 10 launching vehicles separately. So there will be 2 launch for each missions. And then the lander and the spacecraft and the spaceship will have a rendezvous and docking on the lunar orbit. And the astronaut will transfer from the manned spaceship and to the lander, and then make a separation, and the lander will be landed on the surface. After the explorations on the lunar surface, the astronaut will take off using the upstage of the landers to the lunar orbit and make the second rendezvous and docking with the manned spaceship and transfer to the ship and then back to Earth. So in this mission design, you can see that there are about 2 rendezvous and docking operations in one mission. These are just animations of landing, sampling, and also cruising. Chinese government attach a great importance for international collaborations. We have already implemented the collaborations with UN-USA, so each member countries of UN can collaborate with Chinese space station programs. For the cooperation network, we build collaborations with agencies like ESA, DLI, CNES, SOPACO, and also others for the bilateral cooperation. And we also set up collaborations with international organizations like IAF, IAA, APOSCO, and also UN for the multilateral collaborations. For upcoming opportunities, there are scientific research, the flight opportunities, the astronaut training, and also onboard Chinese space stations, and science population educations. For the collaborations, we are not just only collaborate with the spacefaring nations, but also we will provide the opportunity to the new new emerging countries and developing countries for their capacity buildings. As for the lunar manned missions, we will provide a new platform for the scientific explorations and international cooperation. We hope to actively carry out exchange with other countries and seek cooperation opportunities. In my view, to build a community with a shared future of mankind in space, we need a collaboration. Collaboration not only on ground, but also in space. Collaboration not only just for a profit and market, but also for the resolution of the urgent issues we are facing for. Collaboration not only just for our generations, but also for our children and even long, sustainable future. Let's work together and make it happen. Thank you for your attention.
And thank you, Dr. Li Ming. I'm really excited about manned lunar exploration mission and looking forward to Chinese landing on Moon by 2013, such a specific timetable. And then, please welcome Professor Zhong Hongen.
Many thanks for giving me a chance to presentation. My dear friends, China Space Station has completed assembly since November 2022. It has powerful scientific research capabilities. Up to now, hundreds of innovative research have been conducted, and future development are planned. I will report one by one. Firstly, is our exploration capabilities. Soaring on 400 kilometers above Earth with 42-degree inclination, our station mass is nearly 100 tons, and its expected lifetime is more than 10 years. It's equipped lots of experiment facilities inside and outside with 12 kilowatts power supply. Normally, there are 3 astronauts on duty. The China Space Station telescope will be launched in the future, running on the same orbit with the station. Its mass is about 16 tons, its optical aperture is 2 meters, and its field of view is 1.7 square degree. It will survey the sky with very high resolution in wide spectrum. Our station has equipped 14 experiment facilities inside and some payload outside. With these facilities and payloads, the research is conducted, such as space life science and biotechnology, material science in space, microgravity fluid physics, and combustion science, fundamental physics in microgravity, and so on. Our capabilities are extendable with the reserved place to install new facilities, such as 5 express racks inside, and more than 50 external payload adapters outside. Our space telescope contains 5 observation instruments and can be maintained in orbit. It will on flagship level in the 2020s to 30s and expected to obtain over 1 billion galaxy images and over 100 million galaxies spectra. We keep applying the latest technologies to promote experiment efficiency, such as telescience, AI, cloud-based technology. To match with the space labs in orbit, we have ground analog systems. It's a high fidelity simulator of those experiment facilities in orbit, as well as data and power supply management subsystems. We also have ground-based matching test labs, including life science labs, material labs, fluid physics labs, combustion science labs. Secondly, is our research progress. We plan to conduct over 60 research plans within 30 research topics belonging to 4 research fields. Here now, 107 research projects have been implemented with nearly 2 tons of experimental equipment and samples uploaded, and nearly 100 types of samples returned. In the field of space life sciences and biotechnology, 4 facilities have been equipped. Lots of advances have been obtained, especially in space cell biology, spatial ecology, space radiation biology, and the research in biopharmaceutical and clinical medicine have significant application prospects. Several research on osteoblast and myocycles has conducted, such as microgravity-induced osteogenesis in impeding, microgravity-affected autophagy. Several research on human embryonic stem cells have conducted, such as vitro differentiation of germ cells. Human embryonic stem cells have conducted. Closed aquatic ecosystem were operated successfully in our station, as well as rice life cycle from seed to seed and regeneration of ratooning rice. 16 kinds of samples for space exposure experiments are conducted, such as nematodes, microorganisms, rice seeds, and biological micromolecules. In the field of material science in space, there are 3 facilities. Lots of advances and important scientific discoveries have been obtained in metal and alloys, functional crystals, and cross-science research. Performance of multiple functional crystal materials are superior to similar ground samples. Many kinds of metal and alloys have completed solidification in space, such as niobium, silicon alloy, titanium, cobalt, gadolinium alloy, nickel, aluminum alloy, and so on. Many kinds of functional crystals have grown in space, such as indium, arsenic, antimony single crystal, high-quality indium celluloid crystal. Metal, alloy, composite materials, lubricating materials, lunar simulant are exposed in the real space environment to test the effect of space environment on those materials. By using the electrostatic levitation experimental rack, the condensation and crystallization mechanisms of early solar system, Chondrule, and CAI were studied. In the field of microgravity fluid physics and combustion science, 4 facilities have been equipped. Significant progress has been made, including the interface behavior of space fluid transport, turbulence transition, boiling, gravitational scaling, granular rheology, and a 3-dimensional colloidal system, microgravity flame dynamics, and the acoustic field effect. Several research on fluid dynamics have been conducted, such as space storage, transport, and interface behavior of a fluid, annular flow conversion map, and instability mode. Several research on multi-phase flow and phase change heat transfer have conducted, such as searching the gravity scale law of pool boiling heat transfer and bubble thermodynamic behavior, the law of interface flow and heat and mass coupling, transmission of complex fluid in microgravity. Several research on soft matter physics and complex fluid have been conducted, such as discovering new phenomena of dynamics and rheological behavior of a 3-dimensional colloidal system, revealing physical laws that affect the particle separation effect. Several studies on combustion science have been conducted, such as revealing the lift-off and blow-off characteristics of low-flow partially pre-mixed flames, discovering flame stability conditions affected by vortices and acoustic waves. In the field of fundamental physics in microgravity, 3 facilities have been equipped. Series of progress have been achieved in ultra-cold atomic physics experiment, high-precision time-frequency experimental system, and space-cold atomic interferometers. The world's first all-optic trap platform in space to achieve both instant condensate is established, capable of supporting scientific experiment on quantum research. A globally leading high-stability space-time frequency experimental system has been built. At the picosecond level, time difference measurement between our station and the ground is achieved. First, highly integrated 2-component called atom interferometer is running in space, and the equivalent principal test with precision 10⁻⁷ is achieved. In the field of space astronomy, our space telescope is currently under development, and we have already developed a series of data processing algorithms, analysis programs, and so on. Thirdly, it's our future development. As the National Space Laboratory, our station is the largest space comprehensive research and expensive experimental platform in China. We plan to conduct more than 1,000 research projects in 10 years. Highly energy cosmic radiation detection facility and many other facilities are planned for exploring the scientific frontier and hot topics in space research. Our door of international cooperation is always open, surely under principle for peaceful utilization, equality, and win-win. There are three ways of cooperation. One is to develop payload. Another is to develop experiment scheme and corresponding modular. The last but not least is to analyze data and sample together. Much cooperation on scientific exploration has successfully completed. Many collaborative projects are currently underway. In conclusion, our lab is open. We welcome the international partners to join to improve the lives on Earth, enable future space exploration, and understand the universe. Thank you.
Thank you, Professor Zhong. I'm impressed by the facility of China Space Station, especially the CSST, because Euclid just reviewed their first piece of its great map of the universe the day before, and we may know universe better with CSST, hopefully. Please welcome our third speaker, Dr. Serena Paroli. Thank you.
Good morning, everyone. So first of all, thank you for inviting me here and giving me the opportunity to explain to this distinguished audience the research activities that we perform at the Italian Space Agency. In particular, today, I would like to tell you a bit of our recent contributions to research related to human health in space and some of our upcoming activities. So in the interest of time, of course, I will not go too much into the details of each experiment, but of course, if anyone has any interest in discussing further, please come talk to me later and I will be more than happy to do so. So to make a very long story short, the Italian human spaceflight adventure started in 1992 with our first astronaut, Franco Malerba, going into space, followed by Maurizio Cheli and Umberto Guidoni. And with Umberto Guidoni, who was the first Italian astronaut on the ISS, we kicked off our ISS research program. Italy, in particular, has a privileged position in terms of access to the ISS because we have two lanes. On one side, we have a multilateral access thanks to our participation to the ESA optional programs as ESA member state. And on the other side, we have a bilateral agreement with NASA, thanks to the Memorandum of Understanding signed in 1997, for which we get part of NASA resources on the ISS for performing research. Over 20 years of activities have seen also the contribution of all the Italian astronauts to building up our research portfolio, and you have here an overview. This year, we also had another milestone, so we participated to the first private mission, thanks to the participation of the Italian Air Force Colonel Walter Villadei to the Extreme mission. And this opened up a new avenue and a new opportunity to explore private commercial operators as opportunities for performing research in space. So to date, we built a wide portfolio of 83 ISS national investigations, thanks to the contribution of the Italian scientific and industrial community. We count over 350 research universities and centers in our collaborations and 16 leading industries in this field. Most of our research is in the field, over 3/4 is in the field of biology and biotechnology and human research. And one of our key aim is to deepening our understanding of the effects of spaceflight on human physiology, having in mind the development of countermeasures to the negative effects, and always having as a final objective translating the benefits to human health on Earth. So our most recent contribution was the research we performed during the EX3 mission. We performed 5 experiments on orbit and 2 experiments on ground. The 5 experiments on orbit were addressing some of the big challenges that we have for human space exploration, so neurodegeneration, response to oxidative stress, and the development of potential countermeasures. Women fertility in space, which is, let's say, a big question mark for the future of human exploration. Radiation risk, of course, so an accurate characterization of the radiation environment to enable the development of risk assessment models that will be key for deep space exploration. Then we performed a feasibility assessment of an intravehicular suit that can be applied as a countermeasure to muscle loss experienced in microgravity. And 2 on-ground experiments based on the collection of biological samples from the astronauts before and after the flight, aiming to the identification of molecular signatures that can help us understand or monitor the effect of the space flight on human health. So looking at the future development of risk assessment models and easy to use, let's say, molecular tests for health monitoring during space missions. We also had another, let's say, important milestone in terms of operations, because all the experiments were ready to fly in about 6 months, and this was, I have to say, quite an achievement considering the time usually needed for doing research in space. Here is 3 of the experiments that we intend to perform in the next year, always in the field of human health. So one is aimed at developing a wearable system for cardiovascular, for the monitoring of cardiovascular parameters, and this is planned for launch with SpaceX 31, so very soon. And next year, instead, we are focusing more on radiation with this wearable device, wearable dosimeter for real-time monitoring of radiation dose received by the crew member, and a self-diagnostics test, saliva test for monitoring biomarkers of immune system impairment and stress levels, which can also be, let's say, is kind of a point-of-care test for facilitating the crew member self-diagnosis. Then here is an overview of what we intend to do next. So we did a lot of work with our scientific research and industrial community to understand what are the big gaps that we have to fill to enable human space exploration in the future, and we identified this area of interest, so deepening our understanding of the effects of the space environment on human pathophysiology, aiming to develop or identify and then develop countermeasures, better understanding the radiation problem, and also in this case, potentially finding countermeasures, enabling the crew to be autonomous in health monitoring, and the implementation of prevention and mitigation strategies, food production and preservation, which is something that we really have to work a lot on, And last but not least, the impact, the psychosocial impact of isolation and confinement on the human performance and health during space exploration. So these are the areas where we are focusing our investments for the near future. And with this, I want to thank you all, and yeah, I'm here for any discussion.
Thank you, Dr. Paoli. Good to know the Italian contribution to ISS. Then, my old friend, Vladimir Pletzer, please.
Thank you. Thank you, distinguished delegates, ladies and gentlemen, and dear colleagues. I'm very happy to be here with you, and I would like to thank, there we go. I would like to thank, of course, the organizer for their invitation here. You see here the title of my presentation, Parabolic Flight, New Opportunities to Benefit Human Space Flight. I was lucky enough to work also at the CSU, the Center for Space Utilization of the Chinese Academy of Science. I was there for 2 years. And before that, I worked for 30 years at ESA in charge of microgravity payload development and also parabolic flight. My point that I want to display today is that parabolic flight, aircraft parabolic flight, will help us to go from low Earth orbit to the moon and eventually to Mars. And you see there in the little drawing, that's exactly what I wanted to show. So what is first a parabolic flight? These are the aircraft, the main aircraft that are used all over the world. You see on the top left the Airbus A310-0G that is used currently in Europe. Next to it, the Ilyushin IL-76 MDK that is used in Russia by Roscosmos. On the lower left, the Zero-G Corporation aircraft, which is a Boeing 727, which is also currently in use. And then to the right of it, a Boeing 767 that we at Blue Abyss, which is my company where I work as a director of space training operation, we will establish that in about a year and a half or so for parabolic flight. What is actually a parabolic flight? Well, from an horizontal flight, the pilot would accelerate, push full thrust to the engine, and same time pull on the stick, on the command, so the plane will gradually climb up. When the climbing angle reaches about 45 to 50 degrees, the pilot switches off the engine. There's no force other than gravity acting on the aircraft. The aircraft is immediately in free fall, even if it continues to climb first due to its initial velocity, and reach the maximum of its trajectory, as you see here for the profile for the A310, at around 9,300 meters, and continue free falling, but this time downward. And when the diving angle reaches 42 degrees, the pilot would again full thrust to the engine and come back to an horizontal flight. So there are 3 parts in this maneuver: the pull-up for 20 seconds with acceleration of 1.8 to 2 G, then the microgravity phase about 22 seconds with the transition phase about 1 or 2 seconds, and then the pull-out with again slightly less than 2 G, 1.8 G again. We repeat this maneuver 30 times per flight, separated by a few minutes, so to give enough time for the investigator to get prepared with their experiment. And this little video should give you an idea. So now we are on board this aircraft, the Airbus A310-0G, on board which we can really recreate zero gravity conditions, so the weightlessness state. And to achieve this, the pilot on board this plane will, from an horizontal flight, raise the nose of the aircraft up to an angle 40 degrees, same time putting full thrust to the engine, so accelerating up to 2G. After about 20 seconds, when the up angle is about 45 to 47 degrees, the pilot strongly reduces all engine thrust, only keeping enough thrust to counterbalance the air drag. At that moment, the plane is in free fall state, that is, the sum of all forces other than gravity acting on the plane is nil. The plane, due to its initial velocity, continues to climb, reach the maximum of the trajectory, and then start to dive down on the other side. When the diving angle reaches 42 degrees, the pilot again will full thrust of all the engine and accelerate for another period of 20 seconds, coming out of this dive and coming back to a normal horizontal flight. Now we are in the beginning of the pull-up phase, so the very first phase, where gradually the weight increases. Now my weight is increasing, is double. So now I'm about 150, 160 kilo.
Of course, it's a little bit heavy to withstand, but you can see my face is now getting a little bit paler because all the blood is actually pulled down. The pilot announced the angle, the climbing out, 20, 30, and now we come to the injection point where all the engines are strongly reduced. You can hear also the noise is slightly reduced, and we start to float. And if I let the plane float, it will float freely in front of me, and you can climb up to the ceiling like that, perfectly in 0G. Now the diving angle are announced 20, 30, and it's about time to come back on your feet for the pull-out, which is the other part, the other phase of 2G when the pilot accelerates, to come back eventually, ooh, this is getting heavy, to come back eventually to a 1G flight. Wow. And again, during this pull-out, acceleration can reach up to 1.8 to 2G, and our normal weight is then doubled with respect to the apparent weight on Earth. Hey, we are back on an horizontal flight, ready for the next parabola, which will take place in about 2 minutes. So we repeat this sequence of parabola to reach a maximum of 30 parabola in total. And during these 30 parabola, we have up to 10 minutes of microgravity. We perform 3 flights within the campaign, so that gives us 30 minutes of 0G. And if we have 3 campaigns per year, that is equivalent to 1 orbit around the Earth, equivalent to a space lab type of orbit around the Earth, or the type of microgravity time we have on board the International Space Station.
So you see, it's a very useful tool. So we did thousands and thousands of experiments, several thousands of experiments all over the world, in Europe, in the States, in China as well. And you see here, for example, some Chinese investigator who came visit us and prepare some experiment. I'm happy also to see my longtime friend Giuseppe Zumo here, who participated also with several tens of experiments during these flights. He will tell you a little bit more about it. Why is it important? Well, basically, among all the experiments we did in physical science, combustion science, fluids physics, and so on, we did also a lot of research in life science, mainly biology, but also very importantly in physiology, human physiology. Why is that? Because the human body is very well affected by microgravity, the absence of gravity. And the astronauts, during their space flight, either short-term mission or the long-duration mission or future mission to the moon and eventually to Mars, suffer from several, well, malfunction basically. First, the inner ear system is well affected, and most of the astronauts, if not all of them, are sick for the first few days whenever they encounter 0G, and they stay there for quite. It's not like during parabolic flight for 20 seconds, but for several days. And after 2-3 days, well, they're still a bit sick, a bit nauseous, and usually we do not prescribe too much work during these first 2 days. Then the cardiovascular system is, of course, very much affected because all the body fluid will shift upward, and there's some sort of hypervolemia in the head, basically. So that would affect also the brain. So the brain is affected and will work slightly differently in 0G. Most important as well, all the bone will lose calcium and will suffer demineralization after a certain time in terms of weeks or months. And we realized recently, that means about the last 10, 15 years or so, that the vision is affected. So the eye, the organ of the eye, is affected and somehow compressed, probably due to the body fluid shift. So there is too much blood, let's say, than normal in the head, and that would affect the vision as well. So the near-term vision would, let's say, be affected, would be degraded, while long-term vision could be slightly increased, slightly improved. By studying this, not only on board space station, but also on parabolic flight, where there we could do experiment on a larger number of subjects to prepare for future space flight, we can then achieve a better knowledge of how space flight would affect human. And it's only that would allow then to explore, to prepare the exploration of the moon and eventually Mars as well. So I thank you for your attention, and if you have any questions, I would be happy to answer them.
Thank you, Vladimir. And last but not least, Dr. Giuseppe Zumo.
Okay, thank you. Thank you, Dr. Chang, for your introduction. So how can I move? Okay. So this is my presentation. I'm going to present you the Baridi Sana project. It's a project dedicated to study two-phase cooling system for space applications. So, okay. Let me introduce what is the framework of this project. It's an international project funded by United Nations Office of Outer Space Affairs and CMS. This is a program that gives the opportunity to researchers around the world to access the Chinese space station and also the space for several research. So the name Baridi Sana means very cold, and this is in Swahili language, because in this group of researchers there is also a university, the Machakos University from Kenya. There is also the University of Rome, La Sapienza, and In Quattro is a small Italian startup, and also with the support of and collaboration of Enea. So the project aim is to develop a new and innovative two-phase cooling system for space systems, and to make this test on the Chinese space station. So why we are studying this new cooling technology for space? So the main reason is that for electronic components, the trend in developing these components is going towards the miniaturization of the systems and continuous increase of the power of these systems. So in the last years, in particular, the thermal power density of these components has reached very high values. Just to give you an example, the H100 GPU developed by NVIDIA has a thermal density power of about 70 watts per square centimeter. Just to give you a figure, this value is near the lower range of the thermal power densities of fusion reactors components. So this to explain how it's important to develop a new cooling technologies for this kind of electronic components. And for future, it is expected that for future space systems, the use of this high-power electronics could be very important. And one of the main problem is, of course, how to remove these high thermal power densities in space. So the solution that we found is, or not that we found, sorry, that we propose, is two-phase mechanically pumped loop. So it's two-phase cooling systems. So here you can see in the right upper part of the slide a schematic of this system. It actually is a closed pumped loop with a liquid that is not water. It's not possible to use water. We use a refrigerant with low boiling points between 15 and 35 Celsius degree. So there is a pump that pumps the fluid into a heat exchanger called evaporator. This heat exchanger is put in contact with the electronic component that must be cooled. Then at the exit, so evaporation occurs in this component, and so heat is transferred by latent heat of vaporization. So the higher the power removed, the higher the quantity of vapor generated. So the two-phase flow at the exit of the evaporator, now we have two phases, vapor and liquid, is pumped towards the condenser where condensation occurs, and then the liquid, the fluid, the vapor, come back to the liquid state. So This is a technology that is used for nuclear reactors, for fission nuclear reactors, and for new fusion reactors. It's very efficient and very effective. So why is important, again, to study this kind of technology or cooling system in space? Because there is a strong effect of gravity on flow boiling, in particular on the configuration, on the interaction between liquid and vapor. So as Vladimir said, and we performed in our past 10 parabolic flight campaigns in about 15 years, and we studied flow boiling in several configurations. You can see some pictures, and in particular on the left, on the right part of the slide, you can see the effect of gravity and on flow boiling. So, sorry, okay, so in the vertical pipe, you see it's flow boiling in normal gravity, so on ground. In the first horizontal pipe is in microgravity at the same conditions, of course. And so you can see there is a difference in bubble dimensions. So this affects, of course, not only the flow pattern, but also heat transfer, especially with low mass flow rates. And again, just to give you an idea of the effect of gravity, you can see horizontal pipes in normal gravity and in hypergravity. It was very interesting for us to discover that we had also collected a lot of experimental points in hypergravity as well. And this was a very also interesting results. So parabolic flight can give you the possibility to test this kind of system in normal gravity, microgravity, and hypergravity. So this is also something very interesting. Okay, what are the Baridi-Sana objectives? Of course, we want to test two-phase cooling, a two-phase cooling loop at 0G. In particular, what is important for this project is to have a long period, of course, infinite theoretically, so long period of microgravity. One of the features of parabolic flight is that you have 22 seconds of microgravity. This, for a two-phase cooling system, is a quite short period because transients with this cooling system or this physical system takes minutes. It depends on several parameters. So with this test, with this project, we can have a long time microgravity, and we can measure the effect also in long time, and especially in steady conditions, really steady conditions. So also we are going to study steady and transient thermal loads. Another important aspect is not only steady thermal loads, of course, but also transient in microgravity. Also, we test a new kind of evaporator with a graphene layer. It's also the evaporator itself is a graphite evaporator. And so we are going to measure heat transfer coefficient in microgravity, and this helps us to model heat transfer flow boiling in microgravity steady conditions. So the launch will be next year in maybe June or May, June 2025. Okay, sorry, there is some problem in the slide appearance. So this is on the right part, you can see the experimental loop. It's quite, apparently, it's quite simple. There are a lot of sensors. Anyway, there is a pump, a flow meter, and then the multi-channel micro heat exchanger, so where evaporation occurs. At the exit of this evaporator, the flow is pumped to the condenser where condensation occurs. And then the fluid comes back to liquid state and pumped again in the loop. So here you can see the evaporator and the detail of the evaporation channels. So the evaporator, as I told you, is made of graphite and with a layer of graphene. This should increase the heat transfer coefficient significantly. So the total thermal, there are 3 loops actually. One for the two-phase cooling and the other one for FC72 cooling loop. It's a cooling loop provided by the Chinese space station. And also there is also a small air loop to maintain the pressure inside the two-phase loop for having a constant pressure system. So the total thermal power for the evaporator is 160 watts, and this gives us a heat flux of 25 watts per square centimeter. The flow rate is about 0.5 maximum liter per minute, and the fluid is R245FA. This is a refrigerant that we already tested on board of parabolic flight, very safe for human, and already accepted for this kind of test. So this is the experiment. It's, as I told you, it's quite complex due to the fact that there are about 35 sensors, temperature sensor, pressure sensors, and flow rate sensors. There is also a control system in order to obtain automatic test in microgravity. So at the moment, the phases of the project are already performed, are in green. So the system design has been completed, and all the parts has been bought, and the model was, the engineering model was developed, and then we are completing the flight model assembly. So the next steps are the flight model functional test on ground and environmental test on ground. So actually this will be performed in the next future, I mean next week or next 2 weeks. So these are tests, thermal tests on ground to have a reference for the test in microgravity, and other tests with vibrating table and also thermal vacuum here in Italy. Then this test will also be repeated with the Chinese technical support team in China to qualify the flight model for the final launch. And then, hopefully, if everything is okay, we will have the launch in approximately June of next year, and then experiments. And at the end, we will have data analysis. Unfortunately, the experimental loop will be destroyed after the test, or because it's not possible to let it back to the Earth. So thank you for your attention, and all questions and comments are welcome.
Thank you, Dr. Zoomer. Hopefully, Baradisana will be launched in 2025, and it will be the first Italian experiment in China's space station. And thanks again for your brilliant and inspiring presentation. Because of the time, maybe I will just have some quick questions, and please make sure your answer is short, okay? So, Dr. Li, does China welcome foreign astronauts to work on the China space station?
To be short, the answer is simply yes. And now we are ready to welcome the international astronaut to join the Chinese space station program based on the principle of mutual respect, mutual benefit, inclusiveness, openness, and equalities. Thank you.
Okay, thank you. So, and Professor Zhong, will there be new opportunities for cooperation on space payload in the future space station?
We plan to conduct 1,000 research projects in 10 years, and many new facilities and payloads were launched to explore scientific frontiers and demonstrating new technologies. Lots of research places inside and outside the China Space Station are waiting for new experimental instruments. China Space Station is open for the whole world. We have a wide variety of ways to cooperate, including developing payloads and experimental module, data sharing, or other ways you can think. Currently, we have some cooperative projects with NOAA, ESA, and other countries. We can cooperate in a wide range of research areas, such as life science and biotechnology, space material science, microgravity fluid physics, combustion science, astronomy, such as the China Space Station telescope, and HERT, and Earth observation, and the future, the manned lunar exploration. So welcome to join the China Space Station to conduct research you want, and to benefit humankind and explore universe. Thank you.
Okay, thank you, Professor Zhong. Okay, Serena, do you have some expectation or some future idea about cooperate with China?
So let's say that, as you have seen, the international collaboration has been at the core of activities for the Italian Space Agency, and we believe that with the ambition goals that we all have at international level for the future of space exploration, it will be important to act cooperatively overall at the global level. So. Of course, exploring new possibilities is always, let's say, a way to advance better and faster.
Okay, thank you, Serena. Okay, Vladimir, do you have some expectation about the cooperation, international cooperation with China? Yeah.
Yes, definitely. As you saw during my presentation, we are talking about parabolic flight. There are several aircraft used in the world. We will propose a new one in a couple of years, in a year and a half, as I said, and we certainly hope that we could expand also our reach to China. So our idea is first to exploit it in the US and then have a second plane a couple of years later to go abroad, basically, to come in Europe, to come in Middle East, in Asia as well, and then why not come to China? So if you're welcoming us, if you're inviting us, we will come with pleasure to work with you.
Okay, good to know that. Okay, Dr. Zoomer, how's the progress cooperate with China? Is everything okay? And do you have other expectations about the future collaboration?
Okay, yes, cooperating with the Chinese space team or from Chinese Space Agency has been very interesting, very fruitful. So we started in 2019 to develop our experiment for the Chinese Space Station. As I told you, the experiment is complex due to the fact that there is a fluid and thermal power inside the loop, so there are many safety requirements and, of course, as well, experimental requirements to be satisfied. So with the Chinese team, we had a very smooth and helpful collaboration. So we solved actually all the problems on both sides. What I can say as a researcher, of course, these kind of programs are very important to develop and to improve the knowledge in this kind of fields, in my case, heat transfer with phase change. So I can confirm that international cooperation is very important and sharing experience and knowledge and also working together with people from different countries, with different cultures is very important, and everybody can learn and improve our knowledge and better comprehension of other cultures as well. And also I want to mention that also parabolic flights were an excellent system to test this kind of experiments. So I encourage also to have this kind of facility in the future in view of international cooperation with Europe and China.
Okay, thank you, Dr. Zoomer. Okay, last but not the least, I want to thank you, the host Ada, and they want to give some presents to our distinguished speakers. Thank you. And thanks again for your attention of our session and China Manned Space. If you have more questions, please answer the speakers here after wrap up. And so much for our session. Please enjoy your day. Thank you. Thank you.